All right, good afternoon.
Afternoon. Good afternoon.
All right, let's do an attendance ping. I'm just curious who is here at the beginning. I'll do more of these later on. All right, let's start with any questions. Questions on the homework, or questions on the first programming assignment, or questions on what we started Wednesday.
Does it have to be uploaded as a zip or as a tar?
It can be uploaded as a .c file, or if you want, a tar or a TGZ.
Okay.
.cz
If you upload it
is.
to GitLab, you can download a .c file, right, to submit?
You should be able to, yeah.
Do you write it in multiple files with the make file?
You can put it in multiple files with a make file. In that case, you'll have to upload it as a tar. So put all the files into a single archive, and then you can upload that.
So, a tar, not a zip?
What is Canvas set to allow? Do you remember?
Let me check.
I've got a feeling it's .c, .tar, and .tgz. We'll see whose internet gets there first. Yeah, C, tar, or TGZ.
Okay.
And if you don't know how to use tar, make sure you're working with a copy of your files, because if you use tar incorrectly, you can delete your files. So PA1, you've still got until Wednesday morning to submit. So you got some time. All right, other questions? All right, well, let's go back to where we were on Wednesday. We were talking about the product rule. And the product rule had to do with the number of ways to do a task. In terms of the number of ways you can perform a series of subtasks. And so the basic setup, I won't be as formal as I was. You have some procedure which can be done as a succession of two tasks, T1 and T2. And if you can do T1 N1 ways and T2 N2 ways, then the number of ways you can do the procedure is the product, N1 times N2. And so you just multiply them out. And so some examples. You go to a restaurant and you're going to order a lunch consisting of a soup and a salad. And there are 5 soups and 7 salads available. So your task is to order lunch. But we can re-envision that task as a set of 2 steps, 2 operations, done one after another. Task 1 is to choose a soup that you want, and task 2 is to choose a salad. The whole procedure is tell me what you want to eat. But we're going to break it into 2 subtasks. First choose a soup and then choose a salad. Since there's 5 soups, the number of ways we can accomplish this task is 5. Since there's 7 salads, the number of ways we can accomplish that task is 7. Their product is 35. That's how many ways we can choose what to eat for lunch. And sometimes the whole challenge to these kinds of questions is thinking about how you can take what you're being asked to find and represent it as a succession of tasks, as a pair or 3 or more subtasks that you're going to do in order. And so, for example, you have a room with 20 desks, and you have 2 students who are coming in to take a makeup exam. And the question is, how many ways can these 2 students find seats in this room of 20 desks?
Wouldn't it just be 2 times 20?
Could be, but actually not. So if you have 20 desks and all you care about is that they can't sit at the same desk, right, but you have no other restrictions, how many different ways could these students end up sitting? And we can break this into 2 subtasks. Task 1 is having student 1 pick a desk. And then task 2 is student 2 picks a desk.
So that becomes 20 times 20, basically?
Well, it becomes 20 for N1 because the first student, the room is empty, they can pick any desk they want. There's 20 ways that they can satisfy their task. But task 2, the second student picking a desk, while the first student has already chosen a desk, second student can't choose that same desk because you're not allowed to share the desk. So N2 is only 19. So the number of ways 2 students can seat themselves in this room is 20 times 19, which is 380. And so there's 380 different possible seating arrangements. And it's just another version of the soup and salad. Here we have one person, but they're choosing 2 things. First they're going to choose a soup, and then they're going to choose a salad. Well, in this case, whatever soup they choose, they still have 7 salads to pick from. So it's just the number of soups times the number of salads, 35. But depending on the nature of the problem, it may be that, once task 1 is accomplished, task 2 changes somehow. For example, task 1, a student has picked a seat, and so now task 2, there's only 19 seats to choose from. Alright, let's think about student IDs. So a student ID is 9 digits, and the first digit is a 1 or a 2. I'm going to make this easier. I'm going to make a 3-digit student ID. We'll do a simplified version of our Clark IDs. So student IDs are 3 digits. And the requirement is the first digit has to be a 1 or a 2. Alright, so how many ways can we pick a student ID? Well, we can have 3 subtasks. Task 1 is picking the first digit. Task 2 is picking the second digit. Task 3 is picking the third digit. So how many ways can we choose what the first digit will be?
Could just be 2, right? So 1 and 2?
Yep, it's either a 1 or a 2. We've got 2 choices. How many ways can the second digit be chosen?
That'd be 10, right? 0 to 9.
Yep, 0 through 9, that's 10 digits. And the same for task 3. So the total number of ways we can construct a student ID is 2 times 10 times 10, that's 200. So that's the number of student IDs that meet this criteria. And once...
So if you broke it down to like only one person can get assigned each one, the next one would be like 2 times 10 times 9, basically.
Yeah, if you weren't allowed to reuse a digit, right, then these numbers would change. If we couldn't reuse the second digit, then there would only be 9 options for this. And once you see this number, it kind of makes sense, because what are the student IDs that match this criteria? 100, 101, 102, up through 199, 200, 201, 202, up through 299. Those are the only possible student IDs. And each of these is a group of 100. So there's 200 student IDs. right, let's go engineering 250. How many 4-bit strings are there? So we want to count the number of 4-bit strings without using what we know from engineering 250. How could we think about this as a succession of tasks? Any ideas?
Should we think of like how many letters there are in the alphabet, kind of thing?
Yes, but our alphabet here is just the digits 0 or 1. We're picking 4-bit strings, so let me clarify. But yes, same thing, as long as we realize our alphabet consists of just zeros and ones.
Well, from how I see is that each just like letter or digit is independent of the other. So
Correct.
The first one, whether you pick a 0 or 1, will not change how you pick the second one.
Okay.
So you have 2 choices for the first, and since your next choice isn't related to the first, you then still have 2 choices. Then you have 2 choices again, and 2 choices again. So
Okay.
that's 2 times 2 times 2 times 2.
Perfect. So you've done something that you didn't actually state out loud, though. You broke this down into a set of 4 subtasks, right? So this process of finding a 4-bit string is 4 subtasks. T1 is picking the first digit, or bit. T2 is picking the second. T3 is picking the third. And T4 is picking the fourth. And as long as we do these 4 tasks, we've got a 4-bit number. And any 4-bit number can be found by picking, a first, second, third, and fourth digit. And so then you said, the first digit, we can choose that a total of 2 ways. And regardless of which digit we choose, the second digit can also be chosen 2 ways. And so the total number of ways you can do this is 2 times 2 times 2 times 2, which is 2 to the 4th. And that's, something we know from engineering 250. There are 16 4-bit strings. They go from, this to this. And if we write these as integers, this is the integer 0, this is the integer 15. And there's 16 of those. 16 combinations. If you had a truth table with 4 inputs, there'd be 16 rows, etc., etc. If you wanted to know how many 5-bit strings there are, could you do the same thing with 5 tasks and convince yourself that there were 2 to the 5th 5-bit strings? Everybody comfortable that they could do that?
Yeah, you're just adding another subtask, right? Basically.
Just add another T5. You can do that 2 ways. So this will be 2 times 2, 5 times instead of 4. If you had a 100-bit string, could you do this with 100 subtasks and show that there were 2 to the 100th possible such strings? Sure. So here's my favorite question. How would you do this to show that for an n-bit string, there are 2 to the n, where n is any number bigger than or equal to 1? What would we have to do to prove that?
Well, I'd like something like induction. Where
Mhm.
you get so the first or some n task, whether it's like the first or second, something like is this many times. To get to the next step, you simply just multiply it times 2.
There you go.
And you then can show that, this is just 2 to the n. Or this is just, yeah.
Yep. So you could do this with mathematical induction. And you would make a family of propositions P of n, where P of n says, there are 2 to the n n-bit strings. And you'd show P of 1, or maybe P of 4, or, some base case. And then you try to prove that if there are 2 to the n n-bit strings, then there are 2 to the n plus 1 n plus 1-bit strings. And you can do that with the product rule. pick the first n bits and then pick the last bit, and it'll pop out almost without any extra effort. All right, good. Given a set S with n elements, how many subsets can you find? Any thoughts how to envision this question as some sort of succession of tasks that will let us use the product rule? We're doing calisthenics today, right? We're taking a theme and we're just pushing it a bunch of different directions just to kind of build our mental muscles around this concept.
Wouldn't it just be, in this case, it would be n factorial, yeah? Because you can, with n elements, you start off with picking like 1 from n, so you have n, and then the next one you can only pick from n minus 1, and you go down until you're to like only 1 choice left, and that's basically just n factorial.
So that will apply to some of the problems we're going to do, but here we're looking for a subset. So for example, you know, S is A, B, C, and we want to find all the subsets of that. We want to, you know, find this, and this, and this, and so on, and we want to count how many subsets there are. And so we can do something similar to what you said. But say again what do you think the tasks might be that we can perform to create a subset?
Is it, instead is it the idea of, okay, we have 2 different types of sets, one with this element and one without that element.
Mm-hmm.
And then,
Okay.
and then expand that out. So they, of element like 1, you have 2 sets.
Okay, cool. Mm-hmm.
And then you can then expand it out to like a set of 2 elements. You would then have like you then have the 2 sets of like the first element and one without the first element.
Mm-hmm.
And then you can then simply have a case where you then don't have that the second element, which would then just be the first set of subsets, and then you just have then the second set of subsets, which is just the first set plus the second element, which would then be times 2.
Okay, good.
And then you can.
All right, so I think people are getting a good intuition for this. So one of the things with these kinds of problems, we're often asked to tell us how many things there are, how many ways can you do this, how many objects of this type are there, right? To apply a product rule or a sum rule, when we talk about that, to this kind of question, we can rephrase this question like this. How many ways are there to form or to create a subset of S?
Didn't we learn the theorem? It's like 2 to the n possible subsets.
Yeah, we're going to pretend we don't know that theorem though. But you're right. That is what we're heading to. So how many ways are there to create a subset of S? If we have an answer to that, that's the same answer to the question, how many subsets are there? Right? How many subsets are there? Well, let's imagine that we're going to do some procedure that creates a subset, and let's just see how many ways we can do that procedure. That's sort of the language of the product rule now. So one possible procedure for creating a subset is, suppose that we have an ordering on the elements of the set. We have a first element, a second element, a third element. Even though sets are unordered, if we take a particular set, we could say this is, you know, the first, the second, and the third element. Okay, so we can do the following tasks. First, we can say decide whether element 1 is in the subset. Because whatever the first element is, say it's the letter A, if we're building a subset, we've got to decide, are we going to include A or not include A? And then after we've decided that, we should decide whether element 2 is in the subset. And then task 3 will be to decide whether element 3 is in the subset. And so on up through task N, which is to decide whether that last element, element N, is in the subset. And does everybody see that if I perform these N tasks, I will have created a subset? And the number of ways I can perform these N tasks together, that's exactly the number of possible subsets. So if I decide, yes, I'm going to include element 1, no, I won't include 2 or 3, I get this subset. If I decide, no, I won't include element 1, no, I won't include 2, no, I won't include 3, I get the empty set. If I say, yes, I'll include 1, yes, I'll include 2, yes, I'll include 3, I get this subset. So the number of ways I can do this succession of tasks, that's the same as the number of subsets. And how many ways can I complete task 1? Deciding whether element 1 is in the subset or not. How many possible ways can I do that? Right, I have one purpose in life. I'm trying to create a subset of S. I need to decide whether or not A is going to be in that subset. How many choices can I make?
Just 2, right?
Just 2.
Yes or no?
Either it's in there, yes, or it's not in there, no. And for element 2, same thing. Down to element N, which is unfortunately named N, is 2. So product rule says the total number of ways I can complete all these tasks, which is creating a subset of S, is just 2 multiplied by itself N times. That's 2 to the N. And yes, that's the rule that we learned when we first talked about sets. All right, so there's another rendering of this fact that the size of the power set is equal to 2 raised to the size of the set.
So, if we were to just approach any one of these problems, how would we know exactly how to create a task to solve the problem?
We don't. This is like physics, right? We'll go through some problems, and I'll confidently show you the solution, and it will probably make sense. But then when you see a different problem, it may be like, well, what does this have to do with anything we talked about? Right? It may look and feel completely different. And so, the product rule itself is pretty simple to state. Multiply the number of ways to do each task, that's the number of ways to do the whole thing. The real challenge with this concept is figuring out how to apply it to different problems. And that's what you get by looking at different problems and trying to do different problems using the product rule. The wiring that takes place in your brain is not about, how to multiply numbers together. It's about how do I see this problem in a way that lets me use the product rule. And it's not obvious in the beginning, but it comes with practice. And, honestly, in this course, most of the ways that you would use this on a test will probably be some way that we've already done it in class. I'm not going to throw something completely from left field at you. Just like, you know, for an induction proof, I wouldn't throw the odd pi fight at you, you know, and expect you to just kind of come up with a way to do the induction step. So you'll probably see the things that we've been doing in class and on future homeworks. That's probably where you'll see things for the exam. But it's a key thing to keep in mind, right? And like I say, for me, this is what physics was. I could understand when the TA did the problem. I could not take a new problem and do it myself. And for me, it was because I just didn't spend enough time going through enough different types of problems, right? I was confident once I saw the TA work out a problem, oh, okay, I know how to do this, and I would just tune out instead of, you know, following through the next 10 problems that they did. But it's just a practice thing. So let's do a few more examples. Suppose you have 52 cards. So playing cards in the deck, and you shuffle them, so you mix them all up. How many possible arrangements are there? In other words, how many different ways can you arrange 52 cards? Too many, good answer. So how do we break this down into a thinking about a set of tasks? Go for it.
I was thinking that you would maybe put them into sets like our problem you just had, and use the same sort of logic to organize them.
Okay.
Organize the task that way, and then we end up with basically the same thing of 2 to the n is the number of subsets you could possibly have for the amount of cards we have here.
Okay, cool. That would work for a task where we said how many, if there's no limit to how many cards you pick, how many ways can you pick a set of cards from a deck? And so we could look at each card and say, is this a card you picked or not? And that would bring us to 2 to the 52. Pretty big number. But a bigger number is if you say we're going to take all 52 cards, but we're going to put them in a particular order. And so we can think of this as how many ways can we choose an ordering for 52 cards. So does that give us any further ideas? There we go. So someone said this in chat. What possible cards can be the first card, the second card, and so forth? So to choose an ordering for a set of cards, we can think of that as a task 1, which is choose which of those cards will be the first card. Which one's going to be on top of the deck. And then task 2, we can choose the second card. Task 3, we can choose the third card, and we can go on down to task 52 where we choose the last card. And after we've done all 52 of these steps, we will have created a particular ordering of this set of cards. And any ordering of cards that you could possibly have could be created by performing these 52 steps in particular ways. And so now we can think of this problem, how many possible arrangements are there, as a new problem. How many possible ways can we perform this set of 52 tasks? And there, you know, it's cherry picked, it's a product rule problem. All we have to do is figure out how many ways we can do each of these and multiply them together. So what is N1 here? How many ways can we choose the first card to put in our arrangement of 52 cards?
It would be 52 different ways.
We got 52 different ways because we got 52 cards. We haven't picked any of them yet. We can pick any one of those 52 that we want and say, this is the first card. Alright, and remember, these are done in succession. So first we do task T1. Now we have to do task T2, and we have to choose what the second card is. How many ways can we accomplish that?
61.
51, you got it. Alright, 51, because one of the cards has already been chosen, it can't be the first card and the second card, so we've only got 51 cards left. And now we've chosen 2 cards, we have 3 cards left. So there's 50 ways to choose that. And if you work this down, right, this is always 53 minus the number. And so when you get down to 52, there should only be one way to do that. And that makes sense because the last card, that's the only card we haven't chosen yet. We've got a pile with 1 card in it and we have to pick 1 card from that pile. There's only one way to do it, which is to pick that card. And so the total number of ways to choose an arrangement of 52 cards is the product of all of these. And that's called 52 factorial. So 52 with the exclamation mark, factorial, that just means the product of all integers from 1 up to 52. And so we'll see a lot of factorials coming up in this unit. That's a big number. All right, and this is similar to a lot of other problems. Suppose you have 5 people. I'm going to call them A, B, C, D, and E. And you want to take their picture with these people standing side by side. And the question is, how many ways can we arrange them? So you got 5 people, they want you to take their picture. They're going to stand side by side, but you know, they could stand A, B, C, D, E, or these first 2 people could switch B, A, C, D, E, or they could go, you know, completely in the reverse order, or they could go, you know, in this order except for the last 2. And so how many possible ways could you arrange these 5 people? Anyone got an instinct for the answer?
Well, this feels like more closer to the card one.
Mm-hmm.
That like there's only 5 people. So you can choose 5 people to be in the first, and there's then only 4 possibilities for the second person. Only 3 possibilities for the third person. Only and 4 possibilities for the fourth person. And then at that point, there's only 1 person left. So
Yeah.
even. Yeah.
This is exactly the same as shuffling cards, except you're shuffling people. So break this down into 5 subtasks. First task, choose who's going to stand in position over here, and then choose who's in the next spot, and the next, and the next, and who's on the right. And you got 5 ways to choose who goes in that first spot. Whoever you choose, they're standing there now, so you've only got 4 people left to choose who's going to go in the second spot. And then 3 and 2 and 1, and this is good old 5 factorial. So Monday or Wednesday we'll talk specifically about problems like this, where we're rearranging things, and we'll have factorials coming out of our ears by the end of that. They just pop up because of this product rule. Alright, let's do one more product rule example. Let's think about functions. We've been talking a lot about functions in CSE215 lately. So let's talk about functions here. Suppose we have a function going from a set M to a set N. And suppose that M is a finite set containing little m elements, and N is a finite set containing little n elements. So for example, F could go from the set A, B, C, D, E to the set 3, 5, and 11. Functions can go from any set to any other set. Normally they go from integers to integers or reals to reals, but they could go from any willy-nilly set to any other set, right? So I might define a function that takes each of these elements and maps it to either a 3, 5, or 11. And so, one possible function might be f of a equals 3, f of b equals 5, f of c also equals 5, f of d equals 11, and maybe f of e is equal to 3. That's one possible function. So the question is, how many possible functions are there? And the only thing we know is the number of elements here is little m, the number of elements there is little n. And if we have a function from one set to another, it means for every element in this set, the function maps it to a unique element in that set. So we can break this into a set of tasks. So task T1, and let me suppose, let's just work with this example, and then we'll generalize. So I want to find a function. Well, I found one function just kind of like by thinking about it, but in general, if I wanted to define any function from this set to this set, what do I have to do? I have to do 5 tasks, right? Task 1, choose what f of a is equal to. Right? I gotta fill in this line here. Tell me what f of a is. Task 2, choose what f of b is. Task 3, we find f of c. Task 4, we find f of d. And task 5, we define f of e. And that's what a function is. It's a mapping from each element here to an element there. So if I tell you what f of a, b, c, d, and e are, I've told you what the function is. That is the function. So now the question is, how many ways can I perform this task of choosing what the value of f of a is going to be? Just in this particular case. So how many ways can I choose f of a?
You could, you really only have 3 options, right?
Yeah.
Unless you're allowed to map it to 2 things.
It's got to map to exactly one thing to be a function.
Yeah.
So yeah, I can say f of a is going to be 3, or I could say it's going to be 5, or I could say it's going to be 11. And those are my only choices. So I've got 3 possibilities. And if there's no restrictions on the function, how many ways can I choose what b maps to? Exactly the same 3 choices. And the same thing for f of c, and the same thing for f of d, and the same thing for f of e. And so the total number of functions from here to here will be 3 multiplied by itself 5 times, which is 3 to the 5th. So it's not quite 5 factorial, but it's 3 to the 5th. And so in the general case, if we did exactly the same thing, this would turn out to be n raised to the m. The reason being, we could define this function as m subtasks, and for each subtask we define what our function maps a particular value of m to, and we can do that n ways, and so this will be n to the m. And so one more time, let's suppose we have a function which maps a, b, c, d into the set 0, 1. Well, we could do exactly the same analysis. We would have 4 subtasks, find f of a, b, c, and d, and each of those subtasks would be able to be done 2 ways. We could map to either a 0 or a 1. So the number of possible functions here would be 2 times 2 times 2 times 2, which is 2 to the 4th.
So, what we're kind of getting at here is any mapping of one set to another set is basically the cardinality of the second set to the power of the first set.
Exactly. Yep.
Cardinality?
Yep. You got it. And that's a cool thing to know, but we don't have to know that if we know the product rule, and we can think about making these mappings in terms of tasks, right? This comes out of the product rule. And this is just another way of seeing what we learned in Engineering 250, which is if I have a Boolean function, meaning it maps to zeros or ones of 4 inputs, there are 2 to the 4th possible such functions. All right, so that's the product rule. That isn't quite right what I just said. This says something else, but we'll come back to it again. But 16 possible functions, possible Boolean functions with 4 possible input ranges. So if you have a truth table with 4 rows in it, right, there's 16 possible functions. All right, so that's product rule. Similar but slightly different is the sum rule. And the sum rule, again, it looks at the number of ways to do a procedure. So given a procedure P, which can be done as either task T1 or task T2. Right, in other words, if we can think of some procedure as being accomplished by either doing some task T1 or doing some task T2, and if we know T1 can be done N1 ways, and T2 can be done N2 ways, then the procedure P can be done N1 plus N2 ways. So the product rule says if you can do a procedure as a task T1 followed by a task T2, right, where you're doing both of those, then the procedure can be done the product of N1, N2 ways. But if you can do your procedure as a choice of either T1 or T2, then the procedure can be done the number of ways given by the sum of N1 and N2. And so, for example, choose a soup or a salad. And suppose there's 5 soups and 7 salads. and you're going in for the quick lunch, and your choice for lunch is to choose either a soup or a salad, how many possible lunches can you choose? Well, the sum rule says it's just going to be 5 plus 7 equals 12 possible lunches. And that kind of makes sense. I could choose soup 1, soup 2, soup 3, soup 4, soup 5. There's 5 choices. Or I can forget about the soup and I can choose salad 1, 2, 3, 4, 5, 6, or 7. It's a total of 12 possible lunches.
It's so weird how and keeps corresponding to multiplication and or keeps corresponding to addition.
Isn't that weird? Is that tripping anybody else out besides me? Right?
I
Because
find it so weird.
this is an or, and it's doing an and the product rule is doing an and, right? And it's doing a multiply instead of an add. So yeah, this pops up again and again. And it's you know, this kind of vague idea that like all the stuff is the same. It's just different versions of whatever it is that's actually underpinning all of this. Alright, so let's look at some examples of the sum rule. And I won't go through as many as we did for the product rule, but just to give a few examples, let's say pick an award. So pick a student or a teacher for an award. And let's say there's 100 students and there's 10 teachers. So how many ways can you decide who should get the award? Well, yeah, it'll be 110. So we can think of it as two possibilities. Task 1 is, you know, give the award to a student. Task 2 would be give the award to a teacher. Well, N1's pretty easy to find. If you have 100 students, how many ways can you choose a student to give the award to? That's just 100. If you have 10 teachers, how many ways could you choose a teacher to give the award to? That's 10. And so the total number of ways to do this would be 100 plus 10, which is 110. So the sum rule is almost intuitive to us, without even, you know, necessarily calling it a sum rule. I can do this or that. Well, I can do this 10 ways and I can do that 5 ways, so I've got 15 different ways I can do this or that. And so sometimes you make combinations of these. So let's suppose you're creating a variable in a programming language. And your variable is going to be 2 characters. So it's going to look like that. And your first character has to be a letter. And your second character can be a letter or a digit. And letter is just A through Z. We'll make everything uppercase. And your digit is just 0 through 9. And the question is, how many possible variables are there in this language? In other words, how many ways could we create a 2-character symbol given these constraints? And so we can think of it as a succession of 2 tasks. T1 is choose the first character. And then after we've chosen the first character, we'll perform task T2, which is to choose the second character.
For T2, are we doing like A, or I guess it would be A through Z or 0 through 9, right?
Mm-hmm. Yeah, it's still just a single character, but it could be a digit instead of a letter.
Wouldn't this be a succession of tasks that are ORed and AND, so you have A through Z, and you can only pick one,
Mm-hmm.
ANDed with A through Z, and you can only pick one. For each.
So the first one, yes. So to choose the first character, since the first character has to be a letter, there's only 26 ways to do that. 26 letters in the alphabet. But this task T2, we have a choice to make.
That's going to be A through Z or 0
Ah, exactly.
Okay.
So we can do this by choosing either choose a letter or choose a digit. So how many ways can we choose a letter? 26. How many ways can we choose a digit? 10. Add those together with the sum rule. There's 36 possible ways we can choose the second character. So n2 is equal to 36. So the total number of ways we can perform both of these tasks is 26 times 36. That's the number of variables. Or as someone said in chat, you could write it as 26 times 26 plus 10, and then you can see the sum rule and the product rule like that.
Though I think the sum rule is very intuitive. Like, I was already kind of doing that in my head out before, but it's kind of cool to see it all like put out on paper.
Yeah. And that's a lot of what this course is being able to take things that we kind of see intuitively maybe and formalize them, so that we can do more rigorous things with them. All right, so that's the sum rule. It works nicely with the product rule sometimes. And then related to that is something like a subtraction rule. It's not actually called the subtraction rule. It's usually called the principle of inclusion exclusion, which sounds fancier than the subtraction rule, but that's really what it is. So this is something that we touched on in set theory. If you have two sets, A1, A2, we're thinking finite sets. Two sets, A1, A2, and you want to know how many things are in their union, well, sometimes it'll just be the sum of the number of things in each set, right? If A1 is the set ABC and A2 is the set 1, 2, 3, right, the number of things in their union is 3 plus 3, 6. But if there's any overlap between these sets, this sum is going to be too big, right? It's going to count an element that's in A1 and A2, it's going to count it twice instead of just counting it once. So to this sum, we have to subtract the number of things that these sets have in common. And so we get this kind of quirky rule here which says the size of the union is the sum of the sizes of each set minus the size of the intersection. And so I think we played with this a little bit when we did set theory, and then we had that goofy homework problem with the art students and the grad students and the math students, and we got to mess around with this. But let's see what we can do with this in this context of counting, right, and trying to find a number of ways to do things. And so here's another question. So how many 8-bit strings begin with 1 or end with 0, 0? So you make an 8-bit string. There's your 8 bits. We want to know how many of these either begin with a 1 or end with a pair of zeros. It's a reasonable question, right? And so if there is a string which has this pattern to it, right? There's two possibilities. It could look like this. And how many strings are there that have this form, a 1 followed by any 7 bits? Or equivalently, how many 7-bit strings are there?
Should be 2 to the 7th, right?
Yeah, 2 to the 7th, which is 128. Right? The 1's almost like a red herring. I'm really just asking how many ways can I fill in these 7 blanks with 1s or 0s? Now we could do that with the product rule. We could choose this bit, this bit, this bit. We can do each of those tasks 2 ways. We have 7 tasks. It's 2 times it solves 7 times. But we start to recognize this after a while. There's 128 strings of this form. Now if we have a string that looks like this, that ends with 2 zeros, how many of those are there?
So you mean 2 to the 6th?
Yep, 2 to the 6th, which is 64. So if we add those together, we get 192. But that's not the correct answer to this question. So what's wrong with that answer?
We want to take 2 to the 8th and subtract 192. Because we're looking for that number, not 192.
I think we still want 192. These we're looking for the strings that either begin with a 1 or end with 2 zeros. So there's 128.
I thought it was how many don't.
Oh, okay.
do that.
Yeah, so you'd be right if that was it. But yeah, how many do? The first temptation is to just add these together, but why is that not correct? I thought I turned my phone off. Should I answer spam for everybody to listen to? No.
On a side note, I got to piss one of those guys off yesterday. They told me to go in myself. It was awesome.
That's always bonus points.
I always try to get under their skin so they don't call me back.
Yeah. Yeah, sometimes it's like fish in a barrel. Alright, so someone said this in chat, right? Some of the numbers that we're counting up here also get counted down here. For example, a 1 followed by something with ends with 2 zeros will be counted up here and also counted down here. So this number is too big. So we need to know how many 8-bit numbers begin with a 1 and end with 2 zeros. In other words, what's in the intersection of the set of numbers like this and the set of numbers like that. And if there's a number that belongs to both this pattern and that pattern, it looks like this. Right? That's the pattern of all the things that overlap. So how many things are there of this form? How many bit strings are there that start with a 1 and end with 2 zeros? We got a good wild guess in chat that's perfectly correct.
Be the 1.
Say again?
There's just going to be the 1. There's not going to be any more with that 1 and then 2 zeros.
Well, so I could have this. I could also have this. I could have this.
Oh, I guess that's true. Yeah, you're right. Okay.
So got more answers in chat, which are correct. So what's the formula or the number here? Think of the product rule. 2 to the 5th. Right? Product rule. First pick this bit, then this, then this, then this, then this. You're picking a 5-bit number. 2 ways to do each of those, that's 2 to the 5th, which is 32.
So you're just taking the power of any bit you don't know.
Basically, yeah. But what we're really doing is we're using the product rule. We're saying, you know, for each of these bits we don't know, we're going to have to choose whether it's a 0 or a 1. And we're doing that in some succession. We're picking this bit, then this, then that, then that, then that. And so it's the product of each of those two possible choices. But this is also just another way of saying, hey, how many 5-bit numbers are there? Well, there's 32 of them, 2 to the 5th. We know that from digital logic. So if we think of, set A1 is the set of all numbers of this form, and set A2 is the set of all numbers of this form, this represents the form of all numbers in the intersection. Because any number in this form begins with a 1, so it's in A1, and it ends with 2, 0, so it's in A2. And so the number of things in the union would be the number of things in set A1, which is 128, plus the number of things in A2, which is 64, minus the number of things in the intersection, which is 32. That ends up being 160. That's the answer to our question. 160 numbers that begin with a 1 or end with a pair of zeros. So that's also called the principle of inclusion exclusion, which alliterates nicely. All right. Questions or thoughts about that? All right. So our next concept is the pigeonhole principle. And so pigeonholes are, boxes that pigeons hang out in. So there's 9 pigeonholes. We actually have 10 pigeons in there. And so people have trained pigeons for a long time. They're smart birds. They can be taught to fly particular routes, and so people use pigeons to send messages, from one place to another by putting a little message on their foot or something. And you could train them to fly from one spot to another, and you can build a postal system like this, right? Where you send messages from one side of town to the other using these birds to carry the messages, and then someone can deliver them locally. So a pigeonhole is, kind of a general term now, but it's like a box or, a area where a pigeon would hang out. And so there's this principle called the pigeonhole principle that pops up in discussing counting. And the pigeonhole principle is really easy to state. It's laughably obvious, but it's surprisingly powerful. But here's the hand-wavy version of the pigeonhole principle, right? We've got 9 pigeonholes here, right? So 1, 2, 3, 4, 5, 6, 7, 8, 9. If we only had 5 pigeons, it would be possible that they could each sit in a hole without having to share. Right? We could have a pigeon here, 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 and here. Each pigeon is in one hole, and there's even some empty spots. We can go all the way up to 9 pigeons, and it's still possible they could each be in a pigeonhole without having to share. But as soon as we get to 10 pigeons, you're guaranteed there's a situation like this where you have at least 2 pigeons sharing one hole. And you can come back to this model as we're talking about this, because we'll be talking about it more mathematically, but you can think of this or whatever your favorite model is. It could be cats, in house plants or whatever. But if you have 9 pigeonholes and you have 10 pigeons, you're guaranteed at least one of these holes has at least 2 pigeons in it. And it could be that they have something to say to each other, and all 10 of these could be crowded into one of these holes. That's totally possible. The only thing the pigeonhole principle is saying is that it's not possible with 9 pigeonholes to have 10 pigeons without there being some sort of overlap. there has to be at least one box that has 2 birds in it. All right, does that make sense to everybody?
Now, could you make a statement like, not all the pigeons want to be in the box, and make it kind of a little bit more of a complex issue?
That would complicate it, but yeah, we're going to assume that each pigeon is going to be in a box. And if it becomes optional, then it becomes either a simpler question or a problem in quantum mechanics. I'm not sure which. Or quantum computing, maybe.
Alright.
So this is the intuition we can kind of keep in mind if we like, assuming we don't mind thinking about pigeons. But let me give you a little more formal statement of this. So if k is an integer and it's bigger than 0, so it's a positive integer, and k plus 1 objects are placed in k boxes, then at least one box contains 2 or more objects. So if you have k boxes and k plus 1 objects, and you're putting objects in boxes, at least one box has 2 or more objects in it. Alright, that's the pigeonhole principle. I had to teach this course for several years before I could spell pigeon. Alright.
Spelling's bad too.
Yeah. I want to put a D in there for some reason, you know. I guess I hear it, pigeon. Alright, so what are examples of this? And again, you know, the principle is easy to state, it's easy to understand. The bigger challenge is how do we apply this rule to a given problem, right? So we'll do some examples of this. So suppose you have 27 people, and you look at the first initial. So if it's Bob, their initial is B. If it's Nick, the initial is N. If it's Barbara, their initial is B, right? So you take 27 people and you look at the first initial of their name. You're guaranteed at least 2 people have the same first initial. Now, how do we show that with the pigeonhole principle? Well, we could create a series of boxes, and I'm going to call these boxes A, B, C through Z. So I have 26 boxes, and now I'm going to take each of these people and I'm going to stand them in one of these boxes based on what their first initial is. So Bob goes in here, Craig goes in here, Zoran goes in here, and so on. And since I have 27 people, when I'm done doing this, I'm going to have 27 people placed into 26 boxes. The pigeonhole principle tells me at least one box will have at least 2 people in it. And those 2 people will have the same first initial because that's why they're in the same box. If they're both in the box Q, it means they both have the first initial Q. So using the pigeonhole principle in this setup, I can prove that, you know, at least 2 people are going to have the same first initial. And again, you know, it's possible everybody in there has a first name that starts with A, and all 27 people are standing in this box. That does not violate the pigeonhole principle, right? My assertion is that at least 2 people are going to have the same first initial. So how many people can come to a party such that no two people are born the same day of the week? So you're doing some kind of interesting party where you're going to give out prizes based on what day of the week somebody's born, and you want to make sure that you don't accidentally have two people born the same day of the week. And what's the maximum number of people that you could possibly invite without having two people show up who are born on the same day of the week?
It would be 364 or 63, depending on what year it is.
Think simpler. I'm looking for day of the week, not.
No, it'd be 7 people. Right?
Yeah. So 360 something if we were looking at days of the year. But for day of the week, it's just Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, Sunday. And
It'd be a pretty lame party.
hey, you know, but you're giving away prizes just for being born on a certain day, so that could be cool.
I guess that's true.
Born on Tuesday, you get a free car, you know. That's good.
There we go.
So you could invite 7 people. Now it's possible, you know, you invite 2 people and they both were born on Sunday and your party's ruined. But what we're saying here is that the most people that you could possibly invite and not have a problem would be 7. And this is again the pigeonhole principle, which is basically saying if you have 8 people and you have 7 boxes, in this case our boxes are going to be, you know, Sunday, Monday through Saturday. If we have 8 people and we try to put them in these 7 boxes, we're going to have at least one box where someone's at least doubling up, which means at least 2 people are born on the same day of the week. So 8 is not possible, but it's possible that we could invite 7 people, and you know, one of them was born Sunday, Monday, Tuesday, Wednesday, and everybody's born on a different day of the week. So the maximum number of people that you could potentially invite without having a conflict would be 7. All right, 20-point homework. How many students can do this homework without giving the same grade twice? So if we have a 20-point quiz, how many students could I have in a class that would take this quiz without guaranteeing that at least 2 students get the same grade?
Be 21.
And it would be, actually, that's what I thought at first, but how many possible grades are there on a 20-point quiz?
We got 0 through 20. Right?
Right, which is actually 21 possible grades. And so if you had 21 students, they could each get the same grade. So yeah, 21. If you want to know that it's possible no 2 students got the same grade. But if you have 22 students, you're guaranteed at least 2 of them get the same grade. So yeah, 21. All right, cool. Yeah, whoever said that was right. So this can seem really kind of you know, sort of ridiculously simplistic, and it seems like the answer is always just one more than some number in the problem, right? But it can come up in some subtle ways. So let's look at a really quirky problem. This is another one of these problems that, like, if I had to come up with this on my own on a test, there's no way, right? But it's a clever application of the pigeonhole principle, so it's worth seeing. So here's a theorem. so for any positive integer n, there is some multiple of m of n consisting of only zeros and ones. But not in binary, right? Just as a decimal number. So for example, positive integer 1, well, that's a number consisting of just a 1, so that's easy. The number 2, if I multiply by 5, I get 10, that's a number consisting of only ones and zeros. If I take 3 and I multiply by, I don't know what I'm going to do here. What's a multiple of 3 that consists of only ones and zeros? I'm going to cheat and pull out a calculator here. So 3 times 37 is 111. So that's a string consisting of just ones and zeros. Oh, someone already got it. Cool. 2 people. 4 times 25 is 100. 5 times 20 is 100. So the theorem is that for any integer that we pick, we can find a multiple which can be written as just, you know, a number containing ones and zeros. Anybody know what it is for 6? So 6 times 185. Good. Someone got it. 6 times 185 will give you just a string containing ones and zeros. All right. This is a kind of cool fact, and it's not at all clear to me, at least, where this comes from or why this should be true. But it is true, and we can prove it, and we can prove it using the Pigeonhole Principle. And this is a little bit of an example of something called a non-constructive proof. We're going to show that there is a multiple of, you know, any integer n consisting of just ones and zeros without necessarily knowing what that multiple is. We're not really going to find a formula that says, you know, for 3 it's 37, for 6 it's 185, for 5 it's 20, or just 2. But nonetheless, we're going to prove that there always is a multiple, and we're going to do this using the Pigeonhole Principle. So this will be our last proof for the day, but it's a good one to leave on. All right, so so we're working with a number n, and I'm going to say consider the following n plus 1 integers: 1, 11, 111, 1,111, 11,111, and so on up to n plus 1 ones. Right? Again, it's not binary. These are just decimal numbers that happen to have, you know, ones and zeros only. So here's n plus 1 integers. And let's make a series of buckets. And I'm going to call this bucket congruent to 0, mod n. I'm going to call this bucket congruent to 1, mod n, congruent to 2, mod n, all the way up to congruent to n minus 1, mod n. And we know that if we work modulo n, there's n possible things that a number is congruent to. Everything from 0 up to and including n minus 1. So I have n boxes, and I have n plus 1 objects. Alright, I'm going to place each object into a bucket based on what that number is congruent to modulo n. So I'm going to take all of these and I'm going to start putting them into buckets. Well, I have n plus 1 objects and n boxes. What does the pigeonhole principle tell me? So pigeonhole principle tells me at least one box contains 2 objects. 2 or more. Whichever one of these boxes contains 2 objects, those 2 numbers are congruent to the same thing modulo n. And each of these numbers, you know, looks like a series of 1s. So maybe my 2 numbers look like this, right? This is this many 1s, this is that many 1s. If these 2 things are congruent to each other modulo n, their difference is congruent to 0 modulo n. So if I take any of those 2 objects that are in the same bin and I subtract them, I will get something congruent to 0 modulo n. So this thing minus this thing will be congruent to 0 modulo n. But this is just a number of the form a bunch of 1s followed by a bunch of 0s. Right? Because this part of the number will subtract off from that and you're left with a bunch of 1s. And so here's a number containing only 1s and 0s. And since it's congruent to 0 mod n, it's a multiple of n. That's what it means to be divisible by n. And so that's a proof that there's always some multiple of n that can be written as just 1s and 0s. But it doesn't really tell us, you know, what that multiple is. But it gives us a procedure for finding it if we wanted to. Right? If we just started taking these numbers and write each of them down modulo n, we're guaranteed eventually we'll find 2 that are congruent to each other. Just take their difference, that's the multiple of n. So just to wrap that up, let's look at our case of, what was the weird case? Let's just pick on 6. So if n is equal to 6, let's just look at things modulo 6. So 1 is congruent to 1. 11 is congruent to 5. 111, let me do some quick binary math. 111 is congruent to 3. 1111 is congruent to 1. And right there we found 2 numbers that are congruent to 1. We didn't have to go through all 7 numbers. But you know, this could have ended up being congruent to 1, 2, 3, 4, 5, 0, and then this one would be forced to be congruent to one of these. But we already found 2 numbers that are congruent to the same thing. And so that means 1, 1, 1, 1 minus 1 is congruent to 0. This is the number 1110, and since it's congruent to 0 mod 6, that means this is divisible by 6. And if you divide by 6, it's 185. So as I said in the beginning, this is a problem that, you know, I don't think I would have ever dreamed up a solution to myself, and I would never ask you to do a problem like this on a test. But it's an illustration of, you know, this seemingly simple concept. N things less than n boxes, you got to double up somewhere, right? But it can lead us to some pretty unexpected and beautiful results. All right, so that does us for today. Send me an attendance note, please, on the way out. And Monday we'll talk about a generalized pigeonhole principle. We can do this with more than just n plus 1 objects and n boxes. We can do it with k objects and n boxes, and the pigeonhole principle tells us something about that. And we'll see some applications of that related to divisibility and primes. And then we're going to start talking about permutations and combinations. So number of ways to arrange things. And this will be kind of a more targeted application of some of these product rule ideas that we were playing with. So we'll do permutations and combinations, and we'll probably finish that up on Wednesday. Maybe go a bit into the next class, but I believe next Friday is a holiday. Don't quote me on that. Yeah.
Hey, can you explain to me about the ones you circled on there with binary 1 equal is logically equivalent to 1. Can you kind of isn't 1? Well, can you explain me how the model works? Because I think I'm not really understanding what you're writing down with the binary tree.
So 1111 is one more than a multiple of 6. I just used a calculator to find that. These are not binary, these are decimal numbers.
Oh, okay. I thought
So,
they were binary numbers.
Yeah, they look like it, but they're not. So 11 is 5 more than 6, which is a multiple. 111 is 3 more than 108, which is divisible by 6,
Gotcha.
and so on.
Oh,
Yeah.
because they look like binary numbers.
I know, right? Yeah, that makes this problem like weird to try to go through sometimes. All right, cool. Have a great afternoon. Hope you have a fantastic weekend, and I will catch all of you next time.
Bye-bye.
All right,
Okay.
bye.
Thanks, have a good weekend.
Thanks, you too.